turning to today's speaker, everybody knows that entanglement is certainly a quantum mechanics effect, but it wasn't an effect that Einstein particularly liked. In a famous paper he co-wrote in 1935, he argued against the idea of entanglement, saying that it required some kind of spooky action in a distant physics in order for it to work. But more and more experiments that we have performed have shown that entanglement actually does work, and it does exist, and it exists quite a ways out from the last experiments I've seen. So how does this apply to such things as information on computing? Our speaker today is hopefully going to speak a little bit about that, but mostly he's going to speak about how Einstein's equations can come from entanglement. And if Einstein were still alive, I'm sure he'd be sitting right here wanting to hear this work. So, Brian, the floor is now yours.
Great. Well, thank you very much for the invitation to come and speak. Yeah, and what I'll tell you about today is something that I think Einstein would have found interesting, one hopes, which is really about understanding the dynamics of space-time, which is captured by Einstein's equations, as originating from something more elementary, something non-geometric. And the way that that process of emergence happens, the way that the space-time appears in the theory, is actually a manifestation of quantum mechanical entanglement amongst some elementary degrees of freedom that have a very different character than local quantum fields in space-time. And so I want to tell you a little bit today about how we're thinking about that problem, and why we're thinking about it, and why it's interesting. Okay. So yeah, I'm at the University of Maryland. We have a joint group there, a lot of people working in quantum information, also working on quantum gravity, which is what I would characterize this subject as. And there's like really a lot of exciting things happening in this field right now. In particular, I'll talk at the very end about the possibility of doing tabletop experiments using engineered quantum systems to test aspects of this story, to sort of probe quantum gravity, not in our universe, but in a sort of toy universe, which may nevertheless give us some insight about the way quantum gravity behaves in our universe. Okay, so this is what we're going to talk about. I want to basically try to explain how this phenomena, I view it as a sort of theoretical phenomena, how it works. It's called the anti-de Sitter space conformal field theory duality. And what it says is the following rather remarkable thing. It says that you can take some kind of ordinary quantum mechanical system, here represented as a ring. Think of it as a ring of particles, strongly interacting particles of some type, confined to one dimension, and going up as time. And the crucial thing about this system over here, it's some perfectly well-defined system that obeys the rules of quantum mechanics, but there's no gravity in that system, at least naively no gravity. So think about this as just sitting in your lab, and we've neglected the effect of the gravitational force because it's just so weak. And the claim, due to Moldacena, is that for special kinds of systems here, if you tune this in the right way and look at the special kind of degrees of freedom, special kind of interactions, that is exactly equivalent to another system which lives in higher dimensions and has a gravitational interaction. Right? So it's like you're taking this ring here and filling it in with this blue disk. So the gravity sort of lives on the inside of this disk. And this is called holographic duality, the idea being that like a hologram, somehow the one-dimensional or two-dimensional boundary encodes a two- or three-dimensional bulk. And I showed here an example in one dimension just for pictorial purposes, but this is a phenomenon that's believed to occur in theoretical models in a variety of different dimensions. And a sort of a cartoon analogy is to a soup can. The label on the outside tells you what's inside the soup, what's inside the can. Okay. But I want to make a point here, which is that the geometry of these disks is a funny kind of geometry. It's actually hyperbolic geometry, shown here by this nice Escher print. So this is the geometry here is where every fish is the same size. And there's actually an infinite number of fishes as you go from the center out to the edge. You can only see them so far because there's finite resolution here. But all the fishes are the same size. So it's like a saddle geometry. It has uniform negative curvature. And so it's very unlike the geometry that we experience, the space-time geometry that we experience in our own universe. So the point must be made clearly at the beginning that this kind of gravitational theory is not the kind of gravity we have in our universe. Nevertheless, I want to argue that it's still interesting to study and understand what's going on in this case. So why should we care about doing this theoretical exercise? The first reason I think we should care is because we don't understand quantum gravity very well. In fact, we don't even really know how quantum mechanics and gravity, whether they have to come together in some way or not. I mean, we sort of suspect they do, but there is little to no direct observational evidence bearing on this question. But what we do have at the present stage is a set of well-posed theoretical puzzles, often related to the physics of black holes, so the infamous black hole information problem, which I'll speak a little bit about later. And then in the case of the early universe, specifically having to do with the formation, the seeding of cosmic structure, and the theory of inflation, there actually the fluctuations of gravity, the quantum fluctuations of gravity could play a role. So for example, when BICEP 2 claimed to have detected these tensor modes, that would have been a manifestation of gravitons that were amplified by inflation and visible in the sky. Now, of course, that discovery turned out not to hold up, but we could actually have evidence for this within a certain theoretical framework in the not too distant future. Okay, so I think, basically the idea here is that quantum gravity is sufficiently complicated that even if nature gives us something different ultimately, it's still worthwhile to understand the physics in as simple a model as we can so that we'll know what we're looking at once we get to those experiments perhaps in a million years. I don't know, when we have quantum computers the size of solar systems. I don't see any reason why it can't happen. The other thing which is very interesting, which touches on the quantum information point that Mark mentioned, is that this physics that we'll talk about here has connections to a lot of other areas of physics, specifically having to do with quantum information science, with quantum computation, and also quantum materials physics, so the physics of interacting electrons, for example. And there's some hope that actually, by thinking through these questions, we can actually make progress on open problems in that domain. So for example, the resistivity of high temperature superconductors is very famously linear in temperature over a very wide range of temperatures for some materials, and we don't have a very clear theoretical understanding of why that is. So it's a wild idea, but maybe because this ADS-CFT gives you such a different perspective on the physics, maybe it gives you a clue or an insight or just some hint about how to think about this problem in a different way. And there has been a little bit of progress here, for example, in understanding the physics of hydrodynamics actually in certain extreme situations, but we're still waiting there. And then finally, to me, maybe the most interesting thing is actually that this toy model of quantum gravity, this universe in a soup can, universe in a bottle, is actually something that we could in principle simulate using engineered quantum many-body systems of the type that people are now constructing to perform quantum computations or other sorts of coherent many-body experiments. And so we could actually, in principle, probe a toy model of quantum gravity in a novel regime that we can't normally access. And so this talk is sort of going to be ADS-CFT from the perspective of what I would call quantum matter, which is the physics of many interacting particles where quantum effects are crucial for the physics. If you like, this is an edible volume of Landau-Lifshitz from the future. This was a cake at my thesis defense. And this is sort of what we're trying to do. We're trying to write this new volume of how entanglement, how quantum entanglement plays into all of the physics that we know and love, and how it can lead to new and interesting phases of matter, new phenomena that we never expected before. And the starting point here, I want to convince you that there's a lot of sort of space for something interesting to happen. So if you have a single spin a half, a single electron, right, then you have two states. Electron can be up or down. If you have two electrons, each with a spin a half moment, then you have four states. They can both be up, one down, the other, or both down. These are distinguishable because I could held the electrons at two different points. So I could just say this is the electron here and this is the electron there. If I had 500 spin a halves, 500 electrons, I'm totally ignoring the motional degree of freedom here. I'm just focusing on the spin. The dimension of the Hilbert space, the total number of possible states the system could be in, is already 10 to the 150. So it's sort of a vast, unimaginably vast set of possible states. And this is only 500 spins. To give you a sense, if you suppose our universe was de Sitter-like, then there's a horizon at the Hubble radius, roughly speaking. and that total radius has this size. And if you use the famous Bekenstein-Hawking formula for entropy of a horizon, you would get the total number of bits that can be stored in our universe is 10 to the 121. So you can't even write down all of the components of the wave function for 500 electrons in the entire universe. In fact, if you fill the whole universe with the best hard drive we currently have, you can only store 10 to the 97 bits. So what this is telling us, what it suggests to me is that we need a different way of looking at the physics of these systems than just thinking them as giant wave functions, giant vectors in some Hilbert space. We need a more physical way of thinking about the physics, which emphasizes what we can measure and what's simple to understand physically, and which sort of hides this exponential complexity that we don't understand. And what this complexity does give us is an incredible richness in different possible phases of matter that can be realized in this set of spins. So I just ask you to imagine a collection of many electrons, they're interacting strongly. You could control the couplings in some arbitrary way. You know, within the different landscape of materials, you have different realizations of systems like this. And we know from that set of experimental data that there's a very rich variety of possible phases of matter that these electrons can realize. Yeah?
The word strong, you're using that metaphorically?
No.
That's the strong force?
No, I just mean it's that these electrons, not that they interact with a strong force, but that their interaction strength is strong compared to other energy scales in the problem.
Yeah.
Because when electrons interact with you, they just sort of look like electrons. So what we want is to make them interact strongly, and then you can get something new.
By dialing up.
Well, so for example, you can compare the kinetic energy to the Coulomb energy. And if you compress these electrons, you can change that ratio. So you change the density of electrons, and you can change the relative strength of these interactions. And then in a crystal environment, there are lots of ways in which you can essentially modulate the strength of interactions relative to other things. One example would be if you have, imagine a triangular lattice, right? So you have like a triangle here, and you have a spin on each side. Suppose for some reason that the spins want to anti-align. That's called an antiferromagnet. Okay, so this one wants to point up, this one wants to point down, but now this one doesn't know what to do. It can point up or down. So that's called frustration, and what it means is that within the same manifold of fixed energy, you have lots of different degenerate states. So it's sort of like these states can then, with a little extra kick, they could organize themselves in an interesting way. And just to give you some examples, we have what are called Fermi liquids. So this is a theory that describes most conventional metals like sodium. In this theory, the electrons are basically behaving more or less like electrons. They're a little bit dressed by the interaction, but they're more or less electron-like. But you also have magnets where the electrons actually insulate, and the low energy degrees of freedom are spin waves, which are actually bosonic excitations. In superconductors, the electrons pair again into bosonic pairs. And then there are actually even more exotic phases of matter that are realized experimentally. One example are so-called fractional quantum Hall states. These are states of matter that occur in 2 dimensions. Electrons confined in 2 dimensions in a semiconductor heterostructure with a strong magnetic field applied. And what you find there is that in some sense, actually, they have very precisely quantized Hall resistivity, Hall conductance. And you find that in some sense, the electron is broken up into pieces, so-called quasi-particles, which actually each carry in some precise sense a fraction of the charge of the electron. So it's sort of like quarks without quarks. And there are many other things. And what I'd like to suggest in this talk is that actually maybe even gravity can emerge in the sense of ADS-CFT, in the sense that you could have a system of electrons with just the right kind of interactions, where the appropriate description of the physics is not elementary electrons, but actually gravitational waves in some other space. So that's sort of the perspective that I bring to this field, because I started my life as a condensed matter physicist, thinking about the strong coupling physics of electrons. And so this is kind of the way that I came into the field of gravity from this point. Okay, so what are we trying to do more precisely? We want to start from some kind of quantum system. In fact, in the case that we understand, it's actually a quantum field theory. But for purposes of this talk, quantum field theory is basically the same as just a quantum mechanical system. The key thing is it doesn't have gravity. And the quantum field theory lives in some sense at a fixed, what we call boundary space-time. And we want to somehow build a higher dimensional space-time from the dynamics, from the physics of this quantum field without gravity. And this dynamical higher dimensional space-time will have gravitational waves in it and all kinds of other, it'll have black holes, it'll have all the features of Einstein's gravity. And ADS-CFT says that this is possible, but ADS-CFT relies on, at least it had its origin in string theory. We don't want to use that machinery. We want to sort of have a more bottom-up approach where we try to understand how the physics of this gravitational dimension could arise in a relatively elementary way. Here are 3 clues that will be important. The first is that in gravity, the Hamiltonian, the energy of the system, is measurable at infinity, in the same way that total charge is measurable at infinity. That is, you sort of look at Kepler's third law, or you look at the deflection of test mass far away, and that tells you the total energy in the system. This is, of course, unlike if you didn't have gravity, where measuring something here would not tell me how much energy was far away. Right? You really need this long-range force. So in some sense, the Hamiltonian is kind of I would say it's sort of like a boundary property. It's a property of the edge of the system. That's already sort of reminiscent of the picture I showed you where the gravity and the bulk came from the boundary. The second important clue is that black holes have entropy. That's the famous Hawking discovery. And that entropy is proportional to their surface area, not to their volume. Here's the proportionality constant. This involves the speed of light, Planck's constant, and Newton's constant, so very famously unifies all these fundamental constants in a nice formula. And so this is also interesting because it's saying that the entropy is like how many states you have. It's the log of the number of states. So it's saying as if the number of states is also proportional not to the volume, but to the area. So kind of the Hamiltonian, or the energy, which tells you about the dynamics, is like a boundary thing. The entropy, the number of states, is also like a boundary, sort of scale with the boundary. So there is a kind of already what we would call holographic character to gravity. That is, it's as if you're generating something 3-dimensional from something 2-dimensional. And the clue then about how to interpret this extra dimension, so to speak, one clue comes from gravitational redshift. So if you have, say, a massive body here, like a star, and you have an atom which in the absence of this massive body would emit light at some frequency, E0. Then if you place the atom in the gravitational potential well, the star, let it emit that photon and let the photon climb away to infinity out of the well, the energy you observe at infinity will be less than the bare transition frequency by this amount, which is the gravitational redshift. So what it suggests is that you should think of the sort of photon climbing out, the different radial positions relative to the star, like corresponding to different energy scales in the theory. So somehow things very near far away from the star are sort of at their ordinary energy, and as you sort of move in closer to the star, somehow the energy is sort of being changed or renormalized in some way. And this will be realized very explicitly in the construction I'll show you in a moment. So here's a goal. I don't really, want you to worry about the details of this equation too much. This is Einstein's equation with a cosmological constant lambda. For us, we need the cosmological constant lambda to be negative and large. That will give you a solution of these equations, which is called anti-de Sitter space. That's where the ADS and ADS-CFT comes from. And what I'm going to show you is a theoretical route to obtaining a linearized version of these equations where you start with anti-de Sitter space and you add small perturbations on top. So you start with this sort of empty, maximally symmetric space-time, and you consider small waves propagating on top of this thing. And what I want to show you in this talk, I want to argue for you, is that the dynamics of entanglement can actually give rise. It sort of forces these waves to obey Einstein's equations at linearized order. And moreover, that these waves must couple universally to stress the energy of matter. So when you see this equation, there'll be lightning bolts around it later, and that means that we've achieved our main goals.
What is E capital?
It's just the variation of this left-hand side with respect to perturbation little h. It's bad notation that I was too lazy to change. It just means you take this equation and you linearize it in perturbation amount anti-de Sitter space. That's a tensor, and that's what this E is. So E is linear in H.
When you say perturbation about the space, are you talking about perturbation about the cosmological constant?
No, the cosmological constant is fixed, but then we consider adding some extra energy, say, into the space. So nth de Sitter space solves this equation with lambda negative and T AB, the stress tensor, equal to 0. And then what we'll say is actually that then you can have gravitational waves. Once you go away from that sort of empty space with only a negative energy density in it, then you can have gravitational perturbations, wave-like objects, that are sourced by the local energy density. Okay, and this is the metric of nth de Sitter space here in a certain coordinate system. You should see that this minus dt squared plus dx squared plus dr, that's sort of like the usual Minkowski metric that you're familiar with. And the trick is that in nth de Sitter space, there's an extra so-called warp factor out front, which basically tells you that the distance and time as you measure at a given radial distance r is actually dependent on where you are. So the further down you go, there's like a potential well, gravitational well, that the further down you go, say time runs slower. That's what would happen here. You have this dt over r. So that means that you make r larger, time is running more slowly.
And why do you take into account the surface term? Is it important?
It's necessary for the variational principle. So this is if you want to fix the metric, say, at the boundary, then you need this term to be present. So this term cancels a boundary term that you get from here that to make the equation of motion. Yeah.
Now, there's no reason why you can't put the plus in front of the dt and put the minus in the other two places, right? I mean, that's just a convention.
Oh yeah, yeah. I'm just using what we call a mostly plus.
Okay.
Mostly plus convention.
Okay.
Because as in life, time is the weird one. So it should have a minus sign in front.
Okay.
That's the reason.
Now, is it important that you have matter in this model, or can you do the same in an empty space?
Yeah, you can do the same. So actually, before we basically here what we get is the equivalence principle that matter couples universally. There's a simpler derivation of just the left-hand side equals 0, which is the sort of source-free equation, and that also goes through. So you don't have to have the matter.
Okay, but in the source-free equation, you will have to take into account the nonlinear shift of the background.
So yeah, this is just all linearized in perturbation. So
you cannot do that in vacuum.
and sorry?
In vacuum, you cannot just linearize it, because if you endow the gravity waves with effective stress energy tensor, that will cause a nonlinear shift of the background on the left-hand side.
I would say here that the stress tensor due to the gravitational waves is quadratic in H.
Yes.
So to leading order in H, to linear order, it doesn't make sense.
We shall discuss it.
Okay, sure. Okay, so here's the path that we'll take. I'm going to start kind of a long winding road. Let's start down here with something that looks nothing like gravity, qubits and tensor networks. This is sort of the entanglement part of the story. And I'll follow this trajectory all the way up to this peak of Einstein equations, and then, once there, you can see even further away peaks like black holes that have interesting properties. And we'd like to understand those objects from this point of view as well. So let's start there. So let's go back to school. We have a single spin. Single spin has two states, up or down. But I can represent that spin in any basis I like. So they could be the spin z states or the spin x states. And for example, the spin x, if I call the spin z as 0 and 1, so I'm already kind of using this sort of computational logical language, just a nomenclature, but it's suggestive. Then in terms of those z states, the state of plus x spin and minus x spin are this linear combination of the z states. So this is just basic quantum mechanics. And I want to represent this state physically, or sort of pictorially, with a diagram, which is I call a tensor network. Here there's only one node in this network, so it's a very simple kind of network. And the idea is you have a blob that sort of represents the tensor, and the tensor has one free index, which has a label alpha. And the idea is this is just giving you the overlap of the state psi with some fixed basis alpha. So alpha could be 0 or 1, it could run over the z states or the plus minus states, and we call it the physical index. So it's just a machine, just like a tensor you're familiar with in GR. It's just a machine that you put in an index, put in a value, and you get out some other value. Oh, oops, wrong way. Now, once we go to 2 qubits, we need to go to many qubits eventually, but let's go to 2 first. Then, as I said before, we have 4 possible states. They can be all up, all down, or 1 up, 1 down, or vice versa. And the principle of superposition holds, so we can consider any possible linear combination of these states. And in particular, you can construct a state like this, which is, say, 0, 0 plus 1, 1. And the square root of 2 just normalizes it. And this is what's called an EPR, Einstein, Podolsky, Rosen, or Bell pair state. And the special property of this state is that you can't think of it. There's no possible way to decompose this as a state of just particle 1 and just particle 2 independent of each other. So there's some necessary correlation that exists in this state here, so that it can never mathematically be written as a tensor product of state on 1 and state on 2. And that's actually the definition of entanglement, the mathematical definition. But of course, we know that this is a sort of real interesting physical phenomenon. So with using a state like this, you can do interesting information theoretic tasks you could not accomplish otherwise. For example, teleportation of quantum information, or related things like cryptographic applications. So that's sort of one of the places that quantum information science starts off. It says, well, what capabilities do I have if I consider these kind of interesting entangled quantum states that I couldn't do with only classical degrees of freedom? So this is sort of this is the basic unit of entanglement, and it'll play a central role in what follows. So let's try to make a picture for this state. The general rule would be I just make a bigger blob with 2 lines. Each line corresponds to one of the qubits, one of the spins. And I want to think about this blob and try to understand its structure. And so one example of a simple kind of state would be an unentangled state, where there was a product. Then the big blob would turn into 2 small blobs with no connection between them. However, this is a special kind of state, as we already saw on the previous slide. Not every state has this form. And so we can ask, okay, we have this general blob, but can we give some structure to this thing to make sense of the physics of this state? So can we see the entanglement somehow? And the idea is we can, as long as we take a network like this and add an extra connection between these 2 subblobs. So here I have now the 2 physical indices and an extra line, an extra link between the 2 blobs. So now instead of being a rank 1 tensor, these are a rank 2 tensor. And the physical wave function, the amplitude, is actually obtained by contracting along this leg here. And so this extra leg that doesn't correspond to a physical qubit is actually called an internal or virtual leg or index. And it's like think of it as like a variational parameter. I can introduce some degrees of freedom here and sum over them. And I can choose how many of them there are. That's called chi, or something called the bond dimension. And this is sort of now the elementary object. So I'll sort of decompose the state of this thing into the state of 2 smaller things, which are somehow contracted or summed together. And I can play this game for many qubits, say n qubits. I have a big blob, and I can imagine decomposing it into a simpler kind of network like this. You may ask, why can I do this decomposition? And the answer generally is that you can't always. So not every state in Hilbert space has a simple picture like this. Or at least it doesn't have a simple picture if you make the sort of information flowing along these lines order 1. If you make them exponentially complicated, then you can do anything. But if you make it sort of order 1 number of states here, then you can't. But physics comes to save us, because physics does not generate for you arbitrary states in Hilbert space. What we have are local interactions. Electrons interact 2 at a time, strongly when they're close, less strongly when they're far away. And that tends, in general, to produce states in nature that have a simpler structure of entanglement. So they're not unentangled, but their entanglement has a relatively simple character, which, if, for example, the electrons were arranged in a 1-dimensional wire, the entanglement between the different spins might be sort of quasi-short range. They're sort of linked only in their neighbors. And so to have this electron be entangled with this one, you have to kind of propagate some distance through this network. So essentially the few body nature of interactions, locality in nature, strongly constrains the kind of networks that you can produce. So what's entanglement? Let's take this network here And imagine I lost part of it behind a black hole or something, so I can't see it anymore. Then what happens is that the state of these two spins is now different than if they were in isolation. It's as if you don't know exactly what these two spins are doing, because it depends on what the spins are doing behind the horizon that you lost track of. So a kind of uncertainty is introduced into the physics of these remaining spins. And that uncertainty can be quantified using an entropy. This is the mathematical definition. Physically, or mathematically, what you do is take a so-called partial trace, which just sort of means, mathematically means just throw away part of the system. Imagine you can't see it anymore. And then you have a density matrix, and you can compute the entropy, the so-called von Neumann entropy of that density matrix. And what's nice about these tensor networks is that you have a bound on this quantity. That is, the entropy can be no larger than the number of bonds that you cut by this surface that cuts the system into pieces. That's here, this red line. So here you see it cuts this bond, and it cuts that bond. And so the entropy of this region, the amount of uncertainty you generate here, can be no more than the number of bonds cut, here 2, times the log of the number of states that flow across this bond. So what I'm trying to convey here is not the precise details of this formula, but that these tensor networks sort of make entanglement have a geometrical character. That is, you can tell how much entanglement, the maximum possible entanglement between 2 different degrees of freedom by looking at how many different connections exist between those 2 degrees. So it has a very appealing physical picture of the quantum state. Okay, that's tensor networks. Let's go on now and talk about them in the context of many-body physics. So here's a kind of thing I have in mind when I say quantum many-body system. This is a quantum spin chain called the quantumizing model. And it has some simple properties. So the Hilbert space, the local space, is 2-dimensional. That's just a spin on every site here. The Hamiltonian, the interaction is local. Here the interaction says I want the spins to align on the z basis. That's where this negative sign comes in. If the spins are aligned, then they have lower energy. And this term says I want the spins to polarize in the x basis. But because those 2 bases are different, that means these terms compete with each other. And so depending on whether this coefficient g here is big or small, you'll have 2 different possible behaviors. The other crucial thing is that there's no gravity here. This is just a quantum mechanics model on a definite fixed space. But this model is sort of interesting. It's one of the simplest models in physics that illustrates a phase transition, a quantum phase transition, in the ground state of some interacting spin system. When this thing g is very small, then you see that the interaction term will dominate, and that will want all the spins to either align in the up direction or the down direction. So there's 2 possible states, and that's what's called a symmetry breaking state. So like a piece of iron is a ferromagnet. It's exhibiting this phenomenon where the spins tend to line up in one direction, and it's very hard for them to switch to the other direction. So there are sort of 2 ground states over here for g less than g small. Now as you increase g, it turns out there's a point at g equals 1 where something dramatic happens. When g is very large, then the spins want to line up in the x basis, in the plus x direction. But you only have 1 state. So here you have 2 ground states, here you only have 1, so something has to happen, because 2 does not equal 1. So something crazy has to happen in this intermediate point, and it turns out in this model it happens at g equals 1. And what you get there is actually a critical point. So like the boiling of water, there's something happening here where there's like a phase change going on. And the system exhibits now long-range correlations. Correlations that weren't present here. You see here the state is actually a product state here, and it's a product state there. But at this critical point, at this quantum critical point, the system has long-range correlations and actually long-range entanglement, meaning that spins here are actually entangled in some way with spins very far away. In fact, the entropy I showed you before has a nice rule. It's if you look at the entropy of a region of size r, which is this S of r, and you look at the entropy of a region of size 2r, then it just increases by a fixed universal amount, which is characteristic of this quantum phase transition. So just a number here. Now I want to try to make this more pictorially useful for us by going to the tensor network story and saying, okay, if we were in this symmetry broken side where the spins either align all up or align down, or in the polarized side where they align in the x direction, both of those states are sort of short range correlated, they're short range entangled. Just the spins look at their neighbors or don't talk to each other at all. And that can be captured again by a network like this, where the spins have some entanglement potentially, but it's sort of short range entanglement. It's most strong with their neighbors, and then gets weaker as you go. But remember I said this clue number 3 was that the radial direction corresponds to energy scale, right? And if you want to have sort of a lot of space, you're going to need to have degrees of freedom at all energy scales. Otherwise, you're kind of going to not have a lot of room to play in. So you want to have a lot of degrees of freedom. And so it makes sense that we should look at the scale invariant point to try to make more progress understanding what's going on. So here's a picture which I claim captures well the physics of that scale invariant critical point. And the structure of the network is a little bit different now. Now you see there's a sort of my original layer up here. But I introduced a secondary layer where I've done a kind of coarse graining. So I've taken sort of 2 spins and turned them into 1. And this second layer is a coarse grained layer, which, if you like, sort of is like representing higher scale features in the microscopic quantum state here. And then I have another layer, which is even more coarse grained, and so on. So actually, this direction here in the network is like corresponding to coarse graining or to a renormalization group transformation. And what's interesting about this network is you see now that there's potentially a lot more entanglement here. Because now, in this network, if I wanted to know the entanglement of a region, say this spin over to this spin, how many bonds do I have to cut? I have to cut this bond and that bond, so the entanglement is a fixed constant value no matter how big the region is. But here, if I wanted to isolate, say, all these spins here from the rest of the world, how many bonds must I cut? Well, there's different possible ways to do it. One would be to cut here and then go across, cut all these and then go up. That's very expensive. It's a lot of bonds. It turns out you can cut fewer bonds if you go down in this network. Cut like that and sort of go to the point where this whole region has been sort of renormalized or coarse-grained to just one or a few sites, then go across and go back up. Here, the number of bonds, this path would correspond to a number of bonds which is linear in the number of spins here. If you go down this way, it turns out to be logarithmic in the number of spins. So it's much smaller. And I claim, without proof, but I claim in many cases we know that this kind of network is a good description of the physics of these scale invariant critical points.
So physically, does it mean that in this situation it is advantageous for the material to have all spins showing in the same direction?
No, so here this would be something you would need for a situation where the spins are sort of undecided about which direction to point in. Mm-hmm. So they're strongly fluctuating, and they don't prefer any simple direction, because that would be a simple product state that we could capture with a small amount of entanglement.
Are you assuming that it's near the critical point?
Yeah, I'm assuming it's actually at the critical point.
And to the right of the critical point on your previous diagram, they will all prefer to point in the same direction.
That's right. So to either the left or the right, this network will work well, and you can just sort of cut it off somewhere. Basically, the idea being once you coarse grain enough, it looks as if the degrees of freedom are not talking to each other anymore. So they may be locally correlated, they may have formed little clusters, but when you zoom out far enough, they look like they're all more or less independent of each other. Okay, and so I think this is already sort of suggestive. It looks like we started with something one-dimensional, but the appropriate description of entanglement in that state looks more like a two-dimensional object, two-dimensional network, where this is one direction and this is another direction. But you notice that the geometry here, if I sort of view this as like a graph geometry, where the distance would be how many links you cross, that geometry is not the geometry of flat space. Okay. So we have this picture now. This is sort of abstract schematic. And I argued for you that this picture encodes essentially the coarse-grained history of the state. And what I want to claim is that this geometry is actually a discrete hyperbolic geometry. And one way to diagnose that is if you compute the length of minimal curves in this geometry, you'll find that they mimic the length of minimal curves in the spatial part of the anti-de Sitter space geometry that I wrote down for you before. Physically, what's going on is you should think of the number of steps here. Think of r, this coordinate r, as like 2 to the number of steps, right? So the number of steps you go down corresponds to r equals 2 to the number of steps. And so the distance here at the short distance scale, the high microscopic scale, is sort of like large. That's where r is small. Then as you go down in steps, you make r bigger, and the effective distance as you go across is smaller because there are fewer nodes and fewer links. Yes?
To us naive people, it looks like you've suddenly lost time.
I don't have time yet.
Okay.
Yeah. In fact, I'm not sure I actually have a slide here about it, but so the way time comes in is you can now actually use this network to define a coarse graining transformation, a renormalization transformation for the Hamiltonian. Right? And the Hamiltonian is what tells you how time moves in your system. Hamiltonian is generator of time translation. So it's
Why?
what
Because
pushes
time and
the
energy are
fission.
conjugate variables.
Exactly. And what you'll find is that as you move the Hamiltonian from one layer to the next, the Hamiltonian also renormalizes in a very precise way so that in a certain precise sense, time runs more slowly for the degrees of freedom down here than it does up there. And that actually follows from this network once you would impose the fact that it's at this critical point.
Thank you.
So what I want to do is sort of zoom out, basically, and I want to say, let's think about trying to, let's think about this. This is a detailed network construction for some particular model, but maybe it's hinting at some more coarse-grained continuous description, where I would have essentially, if I take this line and think of it as a circle, as I had originally, here's the boundary where my spins live. And the state of this boundary is actually encoded in a network which lives all throughout this bulk, which sort of encodes the coarse graining history. And what's interesting is that now the entanglement, the entropy of this region, this state, is related to the length of a minimal length curve in this bulk. So now you're getting entropy, and the boundary is actually not volume in here, not area, but actually length. So that's sort of smelling like you get in this black hole entropy formula in some sense. Okay, I'm going to go quick here. You can have excitations as well. So you could imagine changing one of these tensors a little bit. That would correspond to some excitation in the system. And in fact, you can change it in 2 ways. You could sort of add a small perturbation here, or you could change the network dramatically. So I like to say changing the network is like changing the geometry. Making a small perturbation is like adding a particle, roughly speaking. And in this formalism, we have a way of dealing with that extra excitation entropy as well. So imagine you had, say, 2 particles, 2 degrees of freedom somewhere down in the network, and you're going to perturb them, and you're going to entangle them in some way. It's possible in this framework to account for the extra entanglement that they produce, in addition to the entanglement that's generated by the network itself. And that entanglement just adds in a simple way. So you have the network entanglement, the sort of geometrical entanglement, plus any entanglement you had from the bulk degrees of freedom. So the key point here is just that the total entropy on the boundary is this geometrical part plus the entanglement of the things that are living inside the bulk. And here it is zoning out again. Zooming out again. Hope not zoning out. This is the boundary. This is my region A. I want to know how entangled A is with the rest of the world. And what this formalism is telling me is that the way that I can calculate that, or physically realize that, is to look for the minimal curve, calculate its length, and then add to it any entanglement between bulk degrees of freedom in different regions. Okay, now I'm ready to get to Einstein's equations. We have all the ingredients. I'm going to be a little sneaky here. I'll alert you to the sneakiness, though. I'm going to assume that actually there is a way to coarse grain this network in such a way that I can ultimately think about a smooth continuum space. That's obviously a leap, and we don't know how to do that in complete detail yet. This is connected to the fact that not every quantum system should be like a simple theory of gravity in this empty big space. I mean, in other words, this Ising chain I showed you is not really exhibiting gravitational dynamics. We know that system very well, we know how to think about it, and it's just not that much like gravity. So maybe it's like gravity coupled to 1,000 other light fields so that it looks nothing like the sort of force law you see in our universe. But we think that there are special systems where you actually really would have a sort of simple gravity theory. And I think that this sort of assumption here, this discrete continuum assumption, is where that physics comes in. But I'll just say the tension network motivates the following hypothesis. Suppose I had a system, somehow, where on the boundary of this system, I had a quantum state. And that quantum state was associated to a geometry which had a higher dimensional character. Right? And suppose the rule for calculating the entropy, the entanglement of that boundary region, was simply I look in this geometry here, I find the minimal length curve, I compute its area. That's one term in the entropy. That's the term we talked about from the network. And then also if there are bulk excitations here, like if there's an electron here that's entangled with an electron over there, I should add that contribution because it pierces across this surface. Yes?
Now, in this formula, you said h bar and c equal to 1?
I did, that's
Okay.
right. Yeah.
Just wanted to make sure I wasn't missing anything.
No, you didn't miss anything. Yeah, so I'm going to assume this. Let me just set this as a starting point. This is like an assumption about some set of states have a nice geometrical picture, and that in that geometrical picture, the way you compute entropy, the way you compute entanglement is that you use this geometrical measure. So that's an assumption. And what I claim is that just from that assumption alone, this is a mathematically rigorous statement, that you can actually show that the geometry so obtained would necessarily obey Einstein's equations. How that works mathematically is you consider a small perturbation to the system, start in the ground state. You can argue on general grounds that that ground state, if the system has scaling symmetry, has to be anti-de Sitter space. That's the only space-time with the right symmetry. So we know that the ground state of the theory should be equivalent to this anti-de Sitter space on symmetry grounds. Basically, you see there's a scaling transformation here. If I scale t, x, and r, then this metric is invariant. And so this change in the state on the boundary, the CFT side, the conformal field theory side, should be related to a change in the metric in the bulk and a change in the state of the bulk fields. Then we can use something like the first law of thermodynamics, but adapted to this entanglement setting. You know, I talked about entropy. We know that in thermodynamics, entropy is associated with energy in such a way that changes in entropy times the sort of temperature give you a change in energy. Well, it turns out there's a similar kind of rule here, actually. This is not a conjecture, it's a proven fact about conformal field theories. That it just happens that for special regions, if I choose this region A to be a ball in the boundary, so an interval in 1 dimension, or a disk in 2, or a ball in 3, then small changes in entropy of that ball are related to small changes in energy, not the physical energy, but some kind of weighted energy here. So here I have the energy density. This is the stress tensor of the CFT. The 0, 0 component, this is just the energy density of the theory, with some kind of funny weighting factor. So don't worry about the details here, the message is just that the energy is related to entropy. Entropy is related to geometry, and so what we're going to be able to show is that energy is related to geometry. And that's sort of the essence of Einstein's equations. In fact, you just take this formula, you translate it using our assumption about geometry and entanglement into a precise formula, and what you get is 0. That's like taking delta S minus delta E is equal to 0. 0 is equal to an integral over some region, this region here, of two things. One is the linearized Einstein equation about anti-de Sitter space we talked about already. One is the bulk energy density. And this integral should be 0. Okay. Well, if you know an integral is 0, that doesn't necessarily tell you the integrand is 0. But if you know it's 0 for every possible ball, which we do, then it turns out the integrand is actually 0. And we know that in this case, and so actually this equation here is obeyed for a particular choice of components. So it's like one component, it's a 0, 0 component of Einstein's equations. We can get the other equations, so this is what I already said, if this is valid for all balls, then the integrand vanishes. We can get the other equations by boosting the theory in different directions, so considering the theory moving in some velocity. And then once you have all of those components of the field equations, it turns out the other components are constraints, which means if they're satisfied at the boundary of space-time, they're satisfied in the bulk. And at the boundary, they translate into conservation of energy and momentum. So they're definitely true at the boundary, and so they just propagate at the bulk as constraints.
So,
Yeah,
so now you've essentially used conservation of momentum, right?
yeah.
When you're with the boost, okay.
Yeah, so that's the only ingredients where basically the properties of the field theory, which are conservation of energy and scale invariance. I told you we're working at this critical point. And then this assumption that geometry is encoded, that encodes entanglement geometry. Those two things, one is just a proven fact about field theory, so a certain type, and one is an assumption, imply that geometry has to obey Einstein's equations.
And when you say that the Einstein equations are linearized about the ADS, do you mean that these Einstein equations are valid only for weak gravity?
Yeah.
Okay.
So I'm not saying that it's incompatible with strong gravity. I'm just saying this this analysis is only a first order analysis.
Okay.
Okay, so that's it. There's the lightning bolts. We're done. I'll just briefly mention, I talked about ADS, which is like the ground state. You can also consider excited states, thermal states, with a finite density of excitations above the ground state. Those, it turns out, are related to black holes in ADS-CFT. And we also have a tensor network way of understanding what the black hole looked like in the tensor network language. Roughly speaking, it corresponds to taking this network and chopping it off somewhere. The place where you chop it off is like the horizon. And then there's an understanding of the interior of the black hole as well as some kind of history or record of the quantum system's evolution. So it actually gives a perspective on what the interior of the black hole means physically. And the fact that you can't see the interior is manifested in the boundary by saying that if I clapped in the room when I came in, you have no way of knowing, because that information has been effectively lost. Right? In other words, a chaotic system will thermalize, and that thermalization process is a loss of memory process. It means, in principle, if you reversed all of the directions of all of the particles and ran time backwards, you would see whether I clapped over there or not. But at any practical measurement, you have no way of knowing. And so actually the irreversibility of the horizon is actually related to the physics of thermalization. Okay, so I'm basically done. I want to mention a few directions that we're thinking about now. I didn't talk about experiments yet. But one of the things you can do with this quantum information perspective, this sort of qubit perspective, is try to instantiate this story experimentally in an engineered quantum device. To say, test to what extent the entropy or the energy are related in the way that I proposed. It turns out the tensor network I showed you is particularly well adapted to noisy quantum systems, for reasons I won't have time to tell you about. And so with my colleague Isaac Kim, we're actually optimistic that these sort of tensor networks could be used for practical application to understand some material property in the near-term future. Another interesting thing is that you can, sort of new kinds of experiments that you're led to consider by thinking through the physics of this proposal. One of them has to do with thinking about reversing time. So running time forward and backwards, sort of like a spin echo experiment, but for an interacting many-body system. That, it turns out, is related to quantum chaos. Black holes are very chaotic objects, it turns out. And that's all suggesting a whole new class of experiments that my colleagues and I at Stanford proposed, and now there are already 4 experiments that have been carried out in less than a year and a half. This all has to do with chaos and what's called scramble. Another thing we'd like to do is actually get closer to the physics of our universe, cosmology, de Sitter kind of expansion physics, in this ADS-CFT model. And we're actually working now on a theoretical approach to that problem, which would hopefully let us take some of these information theoretic insights and transfer them into some way of understanding the mysterious physics of quantum gravity in de Sitter space. All right, so the takeaway, there's a new perspective on the emergence of space-time. And what's really interesting, I feel, is that the physics of quantum information, the physics of entanglement, seems to play a very important role in that process of emergence. There's lots of connections to other areas of physics. I obviously talked about quantum materials quite a bit. I talked about entanglement quite a bit. And what's, I think, particularly interesting is that eventually you're going to be able to experimentally simulate quantum gravity in these toy universes. Now, of course, it doesn't mean that this is the way gravity in our world works. Maybe gravity behaves totally differently. But it still seems interesting and worthwhile to understand the physics of these systems. And of course, there are many, many crucial questions having to do with cosmology, the conditions for this discrete to continuous assumption to make sense, that are all active questions that people are thinking about right now. All right, so thank you for your attention. Yeah.
So I wonder if you could say a little bit about inertia and Mach's principle, whether something like that is emerging here.
Yeah, I think,
Has anybody thought about that?
yeah, a little bit. Yeah, so somehow like the motion of particles in this space is related to renormalization group transformation. And so this is like saying that the dimension, the scaling dimension, like how much it renormalizes should be related to its mass. So you do get some notion of mass out, but I think it's not completely clear yet, sort of in what precise sense. You know, this picture that I showed you is, as was already observed, sort of, it feels a little space-like. I mean, time is sort of there, but it's not a very integral part of the picture. So I think we don't deeply understand yet the physics of inertia in this case. But the equivalence principle we do have some understanding of. It has to do with the fact that in the bulk, everything contributes to the entanglement. In other words, it doesn't matter if it's two photons entangled or two electrons, entanglement is entanglement, and they're interchangeable. And that's actually one perspective on why equivalence principle holds.
Could you please get back to your first picture with 1 + 1 minus d and 2 + 1 minus d?
Sure.
So,
All the way. Yeah.
yeah. So d is the spatial dimensions, is that right?
So here it's one spatial dimension and one time dimension.
And y minus d?
Oh, sorry, no, this is
Okay.
just hyphen, not minus.
Okay,
Sorry.
okay. So you add one dimension
Yeah.
on the right, and did I get it correct that according to this conjecture, we are living on a sheet or on a sub-manifold of a manifold of a larger dimension? Is that right?
No, we live in the larger dimension.
We
But
live in a
all
large-
because we have gravity,
Mhm.
right? And all of our physics is encoded somehow at the boundary of space-time. That's what this is saying. Now, of course, we don't live in empty de Sitter space. So here, this boundary, is very different. Actually, if you're in the middle here, you can send a light pulse to the edge of space-time and back in finite time.
So technically, the space-time which we see, is it a boundary of some bigger universe?
No, we would be the bigger universe in this analogy.
So we are the bigger universe.
We are the bigger
But
universe.
we're not in this kind of space.
We're not in this space-time, but you know, if you approximated our universe as de Sitter-like, for example,
Yes.
then there's boundaries at plus and minus future infinity. So like sort of the asymptotic future is a boundary and the asymptotic past is a boundary.
Okay.
So here boundary is sort of like it's spatial infinity, there it's at time-like infinity, so the whole structure of the theory is quite different.
Okay.
But still people want to think somehow that we're all encoded in essence in correlations of, you know, the infinite future and the infinite past in this context.
So the important thing for us is that there exist these boundaries.
Yeah.
Okay.
Yeah, in general relativity in general, the boundaries of space are very important. The Hamiltonian is actually zero in the bulk, meaning there's sort of no evolution, basically because time evolution is just a diffeomorphism, it's just a symmetry, it's just deforming the geometry in some way. So Hamiltonian is always a property of the boundary of the system. This is a known property. Of
Yeah, but that in a way negates the Faddeev and Popov construction, because there you carry out canonical transformation and tacitly get rid of a boundary term.
Yeah, well, so yeah, here's not a boundary term, it's just the boundary itself. And so it's actually saying that the only thing which is left is a boundary term in the Hamiltonian.
Okay.
Yeah.
So if you find a violation, the experimenters find a violation of the equivalence principle, what happens?
Good question.
Do you mean in real space or in some quantum tabletop thing?
In real space.
Yeah, in real space, there's no immediate contradiction with what I said here, since this is not real space.
In tabletop then.
But this is only the first term. So, like this rule here, that the entropy, where did it go? Yeah, this rule, that the entropy is area plus bulk. This assumption here is actually encoding that it's Einstein gravity and not some like higher curvature gravity. So if you modified this, then you would modify the way gravity couples to matter, and that would be one way of sort of changing what happens with the equivalence principle. Also, so there's another way in which this can be modified. So it just means the theory is more complicated. It doesn't mean the whole picture is completely wrong in this sort of imaginary space. Yeah.
So one of the things that gives me trouble about this sort of stuff is sort of the notion of time.
Mm-hmm.
Right, in general relativity, or in special relativity, time is multi-valued, right? Your time is not necessarily the
Yeah,
same
okay,
as my
I see what you
time.
mean, yeah.
Right. Now, it all works out to be causal. In special relativity, certainly, in general relativity, we think, but it's definitely multi-valued. But here, with this entanglement, it seems like the time is actually univalued. Right, there's sort of one underlying time
Yeah.
that's propagating forward, so that because you say, this could be entangled with that. Well, okay, so if I'm zooming by at 0.9 c, those things may
Yeah.
appear to happen at different
Yeah.
relative times, and I don't really understand how that sort of maps from the one to the.
Yeah, good question.
The
So-
triangle, that thing, sort of thing.
So, like one way to say, yeah, this is a great question, and actually something the whole community does not understand fully yet. But in the picture, like, gonna keep going back and forth. So, like, I sort of drew it as if like this spatial slice corresponded to this boundary time.
That looks like a foliation.
Right, it's a foliation, but I could equally well sort of have bumped it up here and then gone down there and anchored at the same time.
And general relativity is not a unique foliation.
Right, and so you can choose any of those things. So the boundary time, even if you anchor the boundary time, which is like this sort of physical universal time that I'm talking about here, there are lots of different bulk times. You can foliate differently, as you say.
And it's not clear how that anchoring would be done either. But
Yeah, so somehow in the CFT state there's redundancy. There's sort of different ways of viewing it in the bulk, which should all be equivalent because they're equivalent in GR, and we don't understand how that works yet in this thing. Even in ADS CFT we don't understand how it works. So this is actually an important open question to understand how the so-called the different foliations of the bulk diffeomorphism
I actually
symmetry.
think that's where there might be in real space, not
Yeah.
10 space, experimental tests, because this is the sort of thing you could do locally. Again,
Yeah.
like going out to
Yeah.
the moon or whatever, you
Yeah.
can have differences in times. You can then say, well, what happens to the entanglement?
Yeah, and in fact, here I sort of glossed over this point, but you really have to be pretty careful about what you mean by points in the bulk, because as you again, point out, like point doesn't really mean anything in GR. Like you can move the point around. You should really have a relative notion. Like it means two photons collided here, so it has some physics meaning.
Events have meaning.
Yeah, events have meaning, and so you have to sort of anchor things to the boundary in a precise way where the geometry is kind of fixed. And so there's a whole formalism for doing that, which you can try to use to make sense of what it means to have different particles here. Yeah.
It's always amazed me that in special relativity, you still have a concept of simultaneity. It may be complicated to teach the students, but you can still teach it. But when you go to GR, simultaneity goes out the window. It really does. There is no simultaneity in classical general relativity. If you believe there is, you're just wrong.
But there is causality.
Just like there is causality.
causality.
There is causality. And the speed of light is really the speed of causality. And the very fact that you have indexes of refraction and crap slows down in solid state is already a hint about what the hell is really going on here.
Yeah, and in fact, this is a whole other talk, which, if you invite me back in a few years, if you weren't too scared off then. Where's this? this metric here, this like if you think of t and x as like the boundary coordinates, then that causality is sort of clear. But there's also causality in the radial direction in time.
Right.
So you can ask, what's the physics of that? And it turns out that has to do with the fact that in this strongly coupled plasma that's on the boundary, things move more slowly than they ordinarily would in free space. And that's slowing down. It turns out to be just enough to make the propagation the bulk causal. So there's a very interesting story there about, which involves quantum chaos and information spreading, which actually relates the experience of an infalling particle, infalling observer, how far into the bulk it gets with how far information is spread on the boundary. And that fact that it spreads more slowly than it could naively have spread in vacuum actually is enough to make causality work.
Well, if there are no other questions, let's thank our speaker again.